We will wrap up Chapter 11 with a discussion on chemical reactions and heat, and relate heat of reaction and an amount of a product or a reactant, and figure out the total heat that is released or needed. First of all, let's talk about some definitions. We have two types of chemical reactions as it relates to heat of the reaction. One is called an endothermic reaction, and the other is called exothermic. In an endothermic reaction, we need to have heat for it to actually occur. And heat is typically written as another reactant. So an endothermic reaction grabs heat from outside, from its surroundings, and it needs that heat to be able to proceed. An example of this would be those ice packs that are used for tight muscles, or when you have pain in your back or something. Inside those packets are chambers that have, well, not this particular reaction here, but they have reactants that are not really in contact with each other. But once you break those, right, you're supposed to break them, and that mixes those reactants together, and then you put it on your back, and it feels cold to you or to us. The reason why they feel cold is because they are grabbing heat from our body, and that heat makes the reaction possible. And as those reactants keep mixing, they will keep grabbing heat from our body, and then we will keep perceiving them as cold. So the ice packs are the endothermic reaction. So an endothermic reaction is occurring, grabbing heat from the surrounding, and heat is treated as another reactant. In an exothermic reaction, exo meaning out, these reactions produce heat. So here's an example of that. Methane burning in oxygen, giving CO2 and H2O, and a lot of heat. In an exothermic reaction, heat is written as a product. We recognize that whether we have an endothermic or an exothermic reaction by the way the heat of a reaction is written, is given to us. If the heat of a reaction is positive, in this case plus 177.8 kilojoules, that plus tells us that it's an endothermic reaction. It needs this much energy for it to start happening. An exothermic reaction has a heat of reaction that is negative, so minus 560.5 kilojoules. So if we see a minus sign, that tells you that you have an exothermic reaction. If you see a positive sign, it's an endothermic reaction. Now, how do we use the heat of reaction to tie it into stoichiometry and the type of problems that we've been covering in Chapter 11? Here's an example problem. We have this chemical equation representing photosynthesis and the heat of reaction, which is given to us in kilojoules per mole. So we have 6 waters plus 6 carbon dioxides, giving 1 mole of glucose and 6 moles of oxygen. Calculate the solar energy that is required to produce 75 grams of glucose. Now, how do I do that? Well, I know that the solar energy is going to be given to me from the heat of reaction. That's the amount that the reaction needs to proceed, and it's going to take that from the solar energy. However, it's in kilojoules per mole. Because it's tied to kilojoules per mole, I can use this amount of glucose that is given to me in grams and convert it to moles. So 75 grams of glucose multiplied by 1 mole of glucose weighs 180.2 grams. So my grams of glucose will cancel. And I take 75 grams times 1 divided by 180.2, giving me 0.416 moles of glucose. Now, since the heat of the reaction is 2803 kilojoules for every mole, to figure out how much energy I need, I will have to account for 0.416 moles, right? So I have 0.416 moles times the heat of the reaction, which is given to me here. So it's going to be 0.416 moles times 2803 kilojoules for every mole. The moles will cancel, and then I multiply those two numbers to give 1.17 times 10 to the third kilojoules for a total amount of solar energy that is required to make 75 grams of glucose. Now, try your hand in this problem. It's basically the same exact one, but we have a different amount of glucose in grams. So convert this to moles and then use the heat of reaction per mole to calculate the amount, the solar energy that is required.